was trying to learn geometric topology of three manifolds because I was interested in hyperbolic three manifolds and in geometry in hyperbolic three manifolds. And it was really hard. The reality is, it was really hard for me, a geometer with all the letters in geometry, to understand the arguments of hyperbolic geometry, which was much more studied from a topological point of view. Although this area is called geometric topology, it has both words in it, like geometric and topology. It's more written for topologists, at least from my perspective, the perspective of a geometer. So I started studying this and organizing it to try to bring a geometric perspective to the geometric topology. So if there are topologists in the audience, I will say I'm sorry, because I will be probably making some hypotheses that I'm not even aware I am making, like piecewise linear and so on and so forth. So, but let's continue, okay? Forward, no. Okay, so some comments. All manifolds here will be assumed to be oriented unless we say they are not oriented. Especially the ambient spaces will always be oriented, but we will have to go through some non-oriented surfaces in the middle of the way. A closed manifold is just a compact manifold without boundary. So it's something you cannot exit. You cannot exit the manifold because it has no boundary and it like closes onto itself. You can never exit a manifold, a closed manifold, just walking around the manifold. And we are interested in three manifolds, and three manifolds are awesome. They are so good because they have this amazing feature that they are homeomorphic to each other if and only if they are diffeomorphic to each other. So sometimes I will use the word homeomorphic, other times I will use the word diffeomorphic, but it's all the same in the context of three manifolds. Of course, they have to be three manifolds. They have to be smooth manifolds, so this happens. And some references for the course are given in this small list. I'm not even sure if I should include my survey in the last of it, but it has other better references there too. But these four books here are like really good and where I took most of our things from. Okay, so let me start with topology and geometry. First, topology basically is the study of shapes. Two objects are regarded as being the same if you can make a deformation one into the other, and not exactly a deformation, more a homeomorphism. And so they are the same object. And that's why sometimes it's called the rubber band geometry, because rubber bands, like you can stretch, you can twist, but they always go back to the start, right? So you have this picture of a sphere, you have this picture of a small sphere, you have this picture of this weird sphere, and you have this picture of this all twisted sphere. And they are just deformations one of the other. So for topology, they are all the same object. For topology, these four examples here are S2. They're just the two spheres. Okay, geometry is a little different. Geometry is the study of smooth objects, manifolds, and the distances in these manifolds, which are called metrics. So from a geometric point of view, these objects are not the same. They are really different because this sphere here, for instance, is large, while this sphere here is small. If you want to go around this sphere, you are walking along this equator, you will take some time to go there. But if you are here in the planet of the Little Prince, you will take a lot less time. So for geometry, these aren't the same. And actually, these other two also aren't the same as this one, because this one, you have this line which is longer, and this other line which is like not so long. And this other one is not even rotationally symmetric. So it's really different from the other ones. And just an intuitive definition, if someone is familiar with the definition of a smooth manifold. A differentiable manifold of dimension n is something that locally looks like a ball of Rn and of the same n for every point. And a metric in this manifold is a way of measuring distances and angles. Okay, so topology and geometry now. We can try to relate them. For instance, how to find the curvature or the radius of the surface of the Earth without leaving the surface of the Earth. This is a topology / geometry question because first, topology is assuming that the Earth is a sphere, and topology is kind of assuming that the Earth separates the universe and you have something inside the Earth and something outside the Earth. So you can talk about radius, and geometry measure this radius and measure something called the curvature of the Earth. So this is a good question. And actually we have this ancient Greek person, I forgot his name, which measured the radius of the Earth with a great, how to say that? Precision, thank you. With a great precision, but he left the Earth. He used the sun. Using the sun, using a stick, is leaving the Earth. So he was kind of cheating. Yeah, he could have done better. I'm joking, obviously, right? But he could have just walked around the Earth, exactly. That would be a good way of measuring, right? So is it possible to measure the curvature of the universe? And what's the topology of the universe? What is curvature? And here I have a very interesting theoretical, intuitional slide for what is curvature. A curvature is something that is captured by geodesics. Geodesics are the paths that light goes on universe basically by an action. I don't know, I am at ICTP, maybe I shouldn't talk about physics here, but yeah. So here we have this pictorial description. If you go to the universe and you have three lasers, three satellites, and you put them in three different points of the universe, and you make a laser ray go from one to the other, one to the other, one to the other, you can measure the inner angles of this triangle. And if the universe has positive curvature, you will see that the sum of these inner angles is not pi, but is larger than pi. If the curvature has almost zero curvature, you will have that this triangle sums up to pi, the angles. And if the curvature is negative, the sum will be less than pi. So this is the intuition of the different types of geometries. You have spherical geometry, Euclidean geometry, and hyperbolic geometry. They are distinguishable by the sum of the inner angles of these triangles made of geodesics along their boundaries. So that's a way of measuring curvature. Okay, obviously, the curvature of the universe is almost everywhere, almost flat, right? As far as I'm concerned. Only mass generates curvature. So this experiment would be interesting if you have like a black hole or the sun exactly in the middle of your triangle. That would be cool to do. Yeah, that's relativity, you know. But okay, so let's relate geometry and topology. And the first question, is the universe compact? And probably no one knows for sure if the universe is compact or not. Maybe it's compact, but just really big from our perspective. And we have some theorems that can easily relate geometry and topology. For instance, this is one of my favorite ones, Theorem of Bohnemeyer's. If you have a complete Riemannian manifold, now complete means that you cannot, you could exit the manifold, but only with infinite energy. Like think of an open disk. An open disk, you can visualize this open disk, and you want to exit this open disk, but you cannot do so unless you go through a path of infinite lengths. That would be a complete metric on this open disk. We will see examples of this kind of metrics eventually. So a complete Riemannian manifold with positive curvature, so not just positive, but bounded away from zero, is always compact and has fundamental group finite. So this is like the best way, the first great way of relating geometry and topology. In blue, we have a geometric hypothesis, positive curvature, and in red, we have two topological conclusions. M is compact and the fundamental group is finite. So I should mention what is the fundamental group just to try to make it the more complete as possible. The fundamental group is the set of non-trivial loops. As I'm using the word set, but it has a structure, it has a group structure. But if you don't know what fundamental group is, just think of all the sets of the set of all the non-trivial loops, circles in an ambient space. Okay, another theorem really cool is kind of the opposite of Bonemeyer's theorem, is Cartan-Hadamard theorem. And if you have a complete Riemannian manifold, but now with no positive curvature, so less than or equal to zero, then we know that the universal covering of this manifold is diffeomorphic to Rn. Actually, it's a little more than this theorem says. It says that the exponential map is a local diffeomorphism. It's a covering transformation over your manifold. So again, you are assuming a geometric hypothesis and you are concluding a topological concluding a conclusion, right? So given a topology, there are restrictions for the matrix. If you have something non-compact, for instance, you can never have a metric in this something non-compact with curvature uniformly bounded away from zero from above. A positive metric, a metric of positive curvature in Rn, no can do. It's impossible by Bonemeyer's. So topology may restrict the matrix, or if you have something whose universal covering is not Rn, then you know that you cannot ask for a metric of non-positive curvature. There will be always points where the curvature is positive in this case, and there will be always points where the curvature is zero or arbitrarily close to zero in the component of this case. And a motivational question would be, given a topology, since there are restrictions for the metric, what is the best metric? That's a fair question, right? Like I'm restricting the topology. So what's the best metric I can ask for in this metric? So let's start warming up one-dimensional case. There are only two topologies for manifolds of dimension 1. You either are compact and then you are the circle S1, or you are non-compact and then you are the line, the whole real line. And I'm thinking here for open manifolds, okay? So I want to, everybody thinks that this picture is okay? Yeah, but why didn't I draw them like this? This is also a circle. This is also a line, but I drew them like this and it's fine. But this is the exception. Most circles aren't like that. This is like the perfect circle. That is like the perfect line because these pictures have constant curvature. This picture appeals to our eyes. We like these pictures because they are more symmetric. So that's maybe a motivation to think that maybe a metric of constant curvature is the best metric. Like I draw something and I draw it with constant curvature by intuition. I don't even know what I'm doing it, but I'm doing it. You ask for a little boy to write a circle, he's gonna write a round circle, right? So that's going to be, sorry? Please mute your microphones. How do you do this? Hopefully people can still listen to me. Did I? I didn't. Okay. So let's go a little farther. Let's start talking about surfaces. Surfaces are manifolds of dimension 2. And we have this natural topology question. What are all, and let's just make a simplification here, orientable and closed surfaces? And this is a question you can actually talk about this question with anyone. Like you are in a party, you are talking to some people with no background in mathematics. You can ask this question. And maybe by the end of the night, you can actually convince the person that there is a reasonable answer for this question. And we can list, the answer is that we can list all the surfaces by the genus, closed, orientable. We have the sphere with this genus 0. We have the torus, genus 1. We have the bitorus, genus 2. And we can just keep adding holes as much as we want. And this is all. Those are all surfaces. And this is reasonably fine. So we can try to make this question a little more mathematical. What are all the building blocks for closed orientable surfaces? And what do I mean by building blocks, right? Well, how do we put these building blocks together? Because that's more or less how you do things in mathematics. You have this object, and then you try to simplify it like a number, a natural number. Now you can divide it into prime factors, and you put these prime factors together by multiplication. Here it's going to be more or less the same. So we can see that this thing with two holes, this bitorus here, is basically two copies of the torus, of the donut. So we have two copies of the torus. We can remove a little disk from each one of them, and we glue them together so it has no boundary. So this is an operation that from two torus creates a bitorus. This operation is called connected sum, and it's actually, torus is the building block for any closed orientable surface, and the operation of putting them together is a connected sum. Here I'm showing a connected sum of dimension 2, but I will talk about connected sum more generally later. So for instance, these three surfaces, they look really different. Even you have to think a little to realize that they are actually all surfaces of genus 3, and that they are all equivalent to 3 times the torus. You pick 3 torus and you glue them together. It doesn't matter how you glue them together. They will be equivalent from the point of view of topology. So they will be diffeomorphic, actually homeomorphic and also diffeomorphic. So they are all built like, take a sphere and you add some 3 tori. And yeah, that's it. And now we can go a little bit, like just put the tip of our toe in geometry and talk about geometrization of surfaces. We know all the surfaces. Now we can return to our original question. What's the best metric? Maybe we can find a metric of constant curvature for any surface. And yeah, that's exactly the answer. Geometrization for surfaces was, well, I'll say this later. So the theorem is this. You take a closed orientable surface of genus G, and so this surface admits a metric of constant Gaussian curvature kappa. So there is a best metric for any surface. And we have some information. We can relate the curvature with the topology. We know that the curvature is positive if and only if you are a sphere, if and only if you are genus 0. The curvature is going to be 0 only for the case of the torus. And the curvature is going to be negative if and only if the genus is bigger or equal to 2. So let's sketch the proof of this. Before I sketch the proof of this theorem, let me just say something. This theorem was first proven by Henri Poincaré, and it was known as the uniformization for surfaces. This is a theorem actually about conformal structures in Riemann surfaces. But this is like today's point of view of this uniformization. Today's geometry, no? Uniformization says the complex surface. But you can really go a little farther. And, no? Okay, so I'm sorry. Okay, all right, but I am attributing to Poincaré this time. Let me just keep going. Okay, so if the genus is 0, we know that we are the sphere, and we have, so let's prove this theorem. Let's just sketch the proof of this theorem. If the genus is 0, then we know that we have the sphere, we are a topological sphere, and we can find a positive curvature metric in the sphere. So it's nothing to do. If genus is 1, you are the torus, and you can realize the torus as a quotient of R2 by 2 translations, like you take one horizontal, one vertical translation, and you have what I call the Pac-Man metric in the torus. You go to the side and you come back to the side. You go from the bottom, you come back to the top. This is going to be topologically a torus, and the metric in this torus, when you push down the metric of R2, is going to be flat. It's going to be 0 curvature. Yeah. Yeah, I know this is confusing. So just so everyone listens, what's your name? Sorry, Hamza. Hamza. Okay, cool. Hamza said that usually the picture of the torus that we have is this picture here of the donut, and this picture doesn't look like flat, and it's not flat, actually. This is an embedding of the torus inside R3, and it's not going to be flat. This flat metric of the torus that I'm talking about, it cannot be realized in R3. It can be realized just in R4 as an embedded torus, because it's S1 inside an R2 cross another S1 inside this perpendicular other R2. So we are inside R4. In R4, the revolution torus would be flat, but in R3, no, you're right. So your confusion is 100% justified. A circle in R2 is also not flat. A circle in R2 is not flat, but when you have a product manifold, the sectional curvature is going to be flat, because this tangent plane, you have only one tangent plane. The parallel transport from here to here doesn't do anything. And then you parallel transport on the other direction, you also don't do anything. And when you come back, when you close this cycle, you'll return to the same point. So that is 0 curvature, basically. So you have this flat metric that comes from this action of R2. And if you have genus higher than 1, so bigger or equal to 2, the thing is you can always cut your surface in some small building blocks, let's call it that way, which are called pair of pants. And the picture kind of describes why they are called pair of pants. This is like the waist, and here are the 2 legs. Here is an example of genus 3, where you can cut it with, here is 1 pair of pants, here is a 2nd pair of pants, then you have the 3rd pair of pants, and the 4th pair of pants. And what's important about the parapants is that you can find an explicit metric of constant curvature -1 in these building blocks. And the geodesic, the boundaries of these building blocks are going to be geodesics. So you can just glue them together, and you see that in the end, what you obtain is going to be smooth, and it's going to have the topology that you want. So this is a little more work to obtain this gluing thing. It's because hyperbolic metrics are really, really, really rigid. They have serious properties.
So this is now negative, like in R3.
Not in R3, no. Not in R3, no. No, they are intrinsically negatively curved. You cannot do that in R3. There are several theorems that would make that impossible. Let me tell you why you cannot have a closed surface of negative curvature in R3. It's quite simple, actually. Actually, you cannot have anything with 0 or less curvature. If it is closed, it's compact, so you will have a farthest point from the origin. Now you take this sphere of this radius. This sphere is going to be tangent to your surface, and the surface is going to be like inside the sphere. So the curvature of the sphere is going to be less than the curvature of the surface. You cannot have something more curved to the outside of something less curved. So this curvature is going to be to this direction, is going to be positive. You cannot have anything with curvature 0 or less, closed, embedded properly, not proper, embedded in R3. Okay. We proved like one way of this theorem. We proved that if you know the topology, then you can find this curvature. And now we want to go the other way around. And it just follows from the Gauss-Bonnet theorem. It's simple. We have that the total curvature of any surface, of any closed surface, is going to be 2 pi times the Euler characteristic. But the Euler characteristic is just 2 minus 2g, where g is the genus. And here, since k is constant, this is going to be just a multiple of the area of the surface. And then you have k times the area, this is positive, it's going to be 2 pi times 2 minus 2g. So if k is positive, 2 minus 2g has to be positive. So the only possibility is if g equals 0. If k is negative, k is 0, then 2 minus 2g is going to be 0. So the only possibility is g equals 1. And if k is negative, then g has to be at least 2. Because we are working in the natural numbers. Genus is a natural number or 0, right? So that's basically the idea of this geometrization. So let's go further. Let's go to 3 manifolds, finally. We could, sorry. For 2 manifolds?
Is 6. Then you said there's some that becomes
yes.
Because we know there are lots. There's no best one.
Okay, yeah, you're right. There are more than one matrix there's a whole bunch of good metrics. You're right. I didn't quite answer the question for dimension 2. This is where things here at the end of the last talk, or maybe at the end of the third talk, we will realize that this raises more questions than answers, but it's so beautiful. But okay, so let's try to ask the question 1 dimension higher. What are all orientable, closed 3 manifolds from a topological point of view? And the typical answer is something more or less like this. I have no idea. I have absolutely no idea how to start tackling this problem. You start thinking, okay, maybe R3. No, R3 is not closed. So R3 is out. Well, S3 is closed. S3 is closed and orientable. And then you start like gaining moment. Yeah, S2 cross S1. Yeah, S1 cross S1 cross S1. And then you realize you have RP3, which is orientable for some reason. And you realize there are fiber bundles over the fine bottom, which are orientable. And you realize you can do quotients, you can do connected sum of these things, and you start to get lost. This question is hard, is what you realize. There is no simple answer for this question. And Henri Poincaré now is the guy that we will talk a little bit about him. He was interested in this kind of questions. And in the early 1900s, he started to study relations between geometry and topology. It wasn't known as topology back then. If I'm not mistaken, it was known as analysis situs. I think it's Latin for something. probably the analysis of the places or something. And one of his main results is the uniformization, which I can see as the geometrization for surfaces, but probably I'm wrong. But so let's just forget this is there, okay? And possibly more importantly, he introduced several concepts in topology, like the fundamental group, like homology groups. And why is this important? Because now we have algebra to help us to distinguish topologies. Once you can attribute a group to a manifold, and this is going to be a topological invariant. If you have two manifolds with different groups, they are different. So this is paramount to the theory. This is really important that he actually started to use group theory to understand topology. And those tools and arguments, well, basically are the foundation of modern topology. There are earlier mentions of topological questions in the works of Euler, of Gauss, but Poincaré was the first one that actually, yeah, let's make topology something. And natural or topology question, because now we can use this word, Poincaré was interested in this question. And even he was confused by it. It was a difficult question. And he tried to simplify the question. When you have a question that is too big, okay, let's try to look at the simplest possible case. And this is the first Poincaré conjecture. The first Poincaré conjecture is not what today we know as Poincaré conjecture. The first Poincaré conjecture is if you have a trimanifold, closed, orientable, with the homology of the sphere, then it has to be homeomorphic to this sphere. Back then, they didn't know equivalences between homeomorphism and diffeomorphism. So this would be actually the question of Poincaré, the first Poincaré conjecture. So basically, what's that saying? It looks like a duck, it quacks like a duck, so it should be a duck. Basically, that's first Poincaré conjecture. But in his paper 1904, 1903, he proved that conjecture is false. It could look like a duck, quack like a duck, but to be a homological sphere. It could be something really complicated with the homology of the sphere, but that is not the sphere. This is the first example of what today we call homology spheres. And this is the picture where Poincaré tried to explain how to construct. To me, it's still a mystery, but it's a cool picture. So I put it there, okay? But in this same page, in the same paper, this is the last page of the paper. First time I've seen this last page of this paper, I got goosebumps, and I actually get goosebumps every time I look at this page. This page is fantastic. The last page, right there at the top of the page, he asks a question. Like the translation for the French there would be, and here is the literal translations. It remains one question to treat. Is it possible that the fundamental group of V, being the closed trimanifold, orientable, reduces to the identity, and yet V is not simply connected? The first time I read this sentence, I was like that, like, what? The fundamental group being the identity is the definition of being simply connected. Today, back in Poincaré's times, being simply connected, he meant being homeomorphic to the tree sphere. So today, this question will translate like this. Is it possible that the fundamental group of V is trivial, and yet V is not homeomorphic to S3? So this is Poincaré's question, which gave rise to the Poincaré's conjecture, which would be the answer to Poincaré's question is no. In other words, if S is a closed, orientable, simply connected trimanifold, then it has to be homeomorphic to S3. So this is the actual presently known as Poincaré's conjecture. It was never made as a conjecture by Poincaré himself. He only made it as a question because he had made his first conjecture and it wasn't true. So I think he was, yeah, let's just make a question now. I would do that. Actually, I wouldn't do this type of conjecture. My God, this is, yeah. Okay, but actually something else that I really like about this last page is Poincaré's remark. Everybody hear about Poincaré conjecture, but nobody hears about Poincaré's remark. And this remark, I really like it. Sorry for my French, but mais cette question vous entraînerait trop loin. But this question would take us too far. And oh God, he was right. I mean, this is the equivalent. I think that this is Poincaré's equivalent to Fermat's. I think I can prove this, but not on this margin. I think this is equivalent, but this is true. Yeah, it's not a lecture. Okay, so, and indeed, this is like the step 0 of this natural, super difficult, now we know, topology question. What are all closed orientable tree manifolds? We don't even know what are all closed orientable simply connected tree manifolds. How can we want to know everything? So of course, today, spoiler alert, we know that Poincaré's conjecture is true, but I'm trying to give you also a historic overview of the whole developments there. Okay, so simplifying a bit. What are all the building blocks? Maybe we can have a notion of what a building block for orientable closed tree manifolds is, and maybe we can try to understand just what the building blocks are. And here's the definition of connected sum for dimension 3. You take 2 oriented tree manifolds, and you take balls in this manifold. So ball is a ball in our tree, topological ball, and embedded balls with their respective boundaries. And you just want to glue these manifolds by their boundaries. But to glue the manifolds together, you are in abstract manifolds. You are not in R3 anymore. So you need to choose something called a gluing diffeomorphism. And this gluing diffeomorphism must be orientation reversal, because otherwise you were like gluing 2 balls to the same side. So you need to reverse orientation so that everything glues back together correctly. Yes, correct. Sorry. Phi should be from S1 to S2, correct. Thanks for that. So M1 connected sum with M2 is obtained by gluing this complement of these balls together using this diffeomorphism. Okay, so officially this is the definition of your connected sum, but and here is the important thing, because you are making a construction depending on choices. You have balls here, you have balls there, you have a gluing diffeomorphism here and there. So it could depend on a lot of things, but the reality is that in dimension 2 and 3, it doesn't. It depends only on M1 and M2, up to homeomorphism. If you choose different balls, if you choose different gluing diffeomorphisms, everything's the resulting is gonna be the same. But this only works for dimension 2 and 3. In higher dimensions, this is a little more subtle to create. So I'm not even, this is a disclaimer, don't try to make connected sums like this if you are a higher dimensional topologist, because it's gonna be a little more messy. So here's the picture. Basically, you have 2 manifolds, you have balls in it, and you glue them together by their balls, and it has basically the visual effect of adding this neck, gluing them together. Okay, yeah. So some properties of connected sum. The first one, the orientation of the connected sum is compatible with the orientation of M1 and of M2. So if they are oriented, your resulting manifold is going to be oriented. It is commutative, it's associative, you have an identity. S3 is the identity element of this operation. And you can think if you have an inverse, and actually you don't. You don't have inverse for this operation because it will always make the resulting manifold more complicated. You can use, presently, you can use Van Kempen's theorem to see that it's a free group. The fundamental group of any connected sum is going to be a free group of the two fundamental groups of your manifolds. So it's always more complicated, or at least equally complicated, if your manifold has trivial pi 1. Yeah. So now we have building blocks. We have an operation, and we can define what is a prime manifold. A prime manifold is a manifold that you cannot decompose it as a connected sum without one of the factors being trivial. So now we can restrict our search to prime manifolds. And you want a decomposition, a standard decomposition by prime factors. And this term was given by Nasser and Milner. Nasser proved the existence of a prime decomposition. Milner proved the uniqueness of a prime decomposition. So the term is what you expect to be. Like if you have a closure-oriented to a manifold, then any connected, any decomposition in connected, then one decomposition in prime factors exists, and it is unique up to reordering and diffeomorphisms of this components. So basically the theorem is whatever, it's exactly what you expect it to be. You have a unique decomposition into prime two manifolds, into prime factors. Okay, let's go a little further. A related definition: an orientable trimanifold is irreducible if any sphere bounds a ball. Why is it related? Why is it different? So let's think a little bit about it. Remember, a prime manifold is something that, let's go back a little bit. A prime manifold is something that you cannot decompose into non-trivial factors. What is a decomposition into non-trivial factors? A decomposition into non-trivial factors, let's go back a little bit longer, too far away, is something that looks a little like this picture over here. This picture shows a sphere. Think of this set as a sphere. It was the boundary of this ball. You have a sphere, and this sphere separates your manifold into two components which are non-trivial. So this is a decomposition, a non-trivial decomposition into factors which might be not prime or prime. So this here is related to the last one because it says that any sphere bounds a ball. If a sphere bounds a ball, then if you want to cut this manifold along this sphere, what you're going to get in this ball is S3. So it is a trivial factor for your connected sum. So they are basically related, but they are different for one example. Oh yeah, any irreducible manifold is prime. That's easy to get, because if you are not prime, you have a sphere. And this sphere is not going to bound a ball either to this side or to the other side. So any irreducible manifold is prime. But now I want to show you this example, S2 cross S1. S2 cross S1 is prime. You cannot make a decomposition of it in simpler factors, but it's not irreducible because you have S2 cross S1. You take any S2 here, it doesn't bound a ball. It doesn't bound anything. It doesn't even separate the manifold. The manifold is still connected if you remove that one from it. So, in fact, this is the unique prime manifold that is not irreducible. And this proof is so cute. I'd like to take a few minutes to show it to you, why this is the unique prime manifold that is not irreducible. So the proof goes more or less like this. If you are prime, but you are not irreducible, you need to have one non-separating sphere. If the sphere separates, you are prime, so in one side it bounds a ball. So if it's not irreducible, you must have a sphere that doesn't bound a ball. So this sphere cannot separate. So this is your sphere. Can you all, this is your sphere. Can you all see the sphere here? Yeah, a little imagination, please. Topology requires a little imagination. This is a sphere. And it's non-separating. If it's non-separating, you have this arc, closed loop, this closed loop that intersects this sphere only one time. Now you need to go clever. You take this parallel neighborhood of S. Think of S as in the middle of the neighborhood. I should use this. Think of S as in the middle of the neighborhood here, and you have copies of S to one side and to the other side. S doesn't separate, but intrinsically it's simply connected. So you can find this notion of a neighborhood of it. And now you also take a neighborhood of the arc, a tubular neighborhood of the arc. Now, in this region here, you know the structure is S, S2, cross 0, 1. It's like a cylinder of one dimension higher. And around this cycle, you also know the topology. The topology is of torus, and then you shrink it to a point. So it's a disk times S1. These two neighborhoods will intersect in two disks, which are cross sections for this disk times S1. And now you use these two disks, you replace in the boundary of this square neighborhood, you replace these two disks by this larger tubular neighborhood. And you see this picture now. This picture, these heavy lines here, they are forming a sphere. Now you have a sphere in your manifold. But this sphere was constructed to separate. It was constructed to separate. And your manifold is prime. So this is a sphere, and this is a separating sphere, and your manifold is prime. Your manifold is prime. You have a separate sphere, it bounds a ball. But it bounds a ball to the outside. That we have nothing, we didn't have any control to the outside. To the inside, we understood everything perfectly. Because we have this S, we have this curve, we have these neighborhoods, everything's fine. But to the outside, we had no control of what was going on. But now we know the outside is a ball. So everything is done because the ball is to the outside of this picture, and the topology on the inside, we understand this topology is exactly S2 cross S1 minus a ball. Because if you make this construction in S2 cross S1, that's the picture. And now you are gluing S2 cross S1 minus a ball together with a ball. And actually, this is a connected sum of S2 cross S1 with S3. And S3, as I told you before, is an identity element. It doesn't do anything when you connect it sum. So your original manifold was already S2 cross S1, as I was claiming. So this is a nice proof. I really like this argument. Okay, so a consequence of this observation, together with the prime decomposition theorem by Nasser and Milner, is that you can decompose not only by prime factors, but you can decompose by irreducible factors and a bunch of S2 cross S1s. And that's how you go. You start reducing, reducing, reducing. And now you have irreducible manifolds. And to classify any three manifold, you just need to understand irreducible manifolds. And I say that as it's something easy, but no. There are still like way too many irreducible manifolds. Okay. So what is this? Is this a recap? Oh, now we start talking about irreducible manifolds. First, let's remember Nasser and Mueller. They gave us a standard decomposition along spheres. And the 60s and the 70s, let's go decompose further. Let's try to decompose by tori. So you can make decompositions by surfaces and you arise at building blocks as irreducible manifolds. And people were seeing, yeah, it's still too complicated. So let's cut now along tori. And several works went into this direction, but the ones that were more famous was by Waldhausen, J. Koechlin, and Johansson. And they found a canonical decomposition along tori, which is called the JSJ decomposition today because J. Koechlin and Johansson. You take now an irreducible, compact, orientable trimanifold with either empty or toroidal boundary. That will be clear. Think of closed trimanifolds for now. I will revisit the toroidal boundary later. Then there exists possibly empty collection of torus in there, such that either each component of when I cut along this tori is either atoroidal, which means that there is no Z times Z subgroup in the fundamental group of this component, or it is Cyphered. Yeah, probably this is not an understandable slide so far of the course, unless you already know the slide. But I need to justify a little bit this slide. Why it took so long for the topologists to reach to this conclusion? Oh, and later we will go farther. We'll go ahead on this decomposition, and we will see that it is also, oh, I forgot to mention, I'm sorry, I need to make a small correction. When I talk about uniqueness of the decomposition of Nasser and Mueller, you need to assume minimality of the factors. You need to assume minimality of the number of factors. You have the smallest one, and that's the canonical. Because you can also add like a lot of S3s in the decomposition. And here's more or less the same thing. When you have a smallest number of tori making a decomposition into this kind of, how to say that, factors of building blocks, then it's going to be unique in some sense. So I was saying something like, it took a long time for them to reach to this uniqueness part and to reach the standard thing. The point is that these spaces, which we will present next, the cipher fiber spaces, they could be further decomposed by tori. And it took a long time for people to understand that they shouldn't be decomposed. They should be left as cipher fiber spaces if you want to understand the topology. Because if you decompose cipher fiber spaces into by tori, you won't see a standard decomposition. It's really more difficult. So it took a while to people to realize, yeah, let's leave cipher fiber spaces as cipher fiber spaces, and then we have canonical decomposition. Okay, so pause on the timeline. Let's go back a little bit to talk about cipher fiber spaces, because this is like one of the most important building blocks. If you understand this theorem correctly, you should think more or less like this. Now we have simpler building blocks with now 4 irreducible manifolds, which are building blocks in some sense. And now we need to understand these manifolds. We need to understand which are the toroidal manifolds and which are the Cyphered fiber manifolds. So let's study Cyphered fiber spaces. Okay, first of all, what will be a Cyphered fiber space? I'm not defining them yet. It will take a while for the definition, but it will be a tree manifold, possibly with boundary, which admits a decomposition by circles. So Cyphered fiber spaces, you will have a notion of a fibration, and this fibration will be by circles. This decomposition will provide the structure of a fibration, which will be called the Cyphered fibration of your manifold. And these spaces were first studied, well, by Cyphered, this German mathematician in the 1930s. And himself, he was saying, I am studying these manifolds because I think they will be an important step towards understanding the whole classification of tree manifolds. Maybe he was just guessing, maybe he had this long insight, but in fact, he was really right. These are really important. And he actually classified all Cyphered fiber spaces up to isomorphisms, which are homeomorphisms that preserve the fibration. So he didn't classify everything up to diffeomorphisms because you have Cyphered fiber spaces, same total space, but with different fibrations. He classified up to isomorphisms. And here is the German term for that he used. I won't try. If someone speaks German can help me out now. No, okay. Okay, sorry, yeah. That's the term Cyphered used. And yeah, as I already said, there are diffeomorphic Cyphered fiber spaces with non-isomorphic fibrations, and that's the extra difficulty to make the complete classification up to diffeomorphisms. Okay, so I am still not defining a Cyphered fiber space. Before I do that, I need to introduce what will be the local picture. So just like a manifold of dimension n, the local picture is always a ball in Rn. In a Cyphered fiber space, we need to look at the local picture, which will be fibrations of the solid torus of D times S1. So I hate this definition. First definition, official definition. Let P and Q be a pair of co-prime integers with P positive, and we can define the standard fibered solid torus TPQ as this. Okay, this is like this. You have a cylinder, solid cylinder, D times 0, 1, and you want to create a torus. So you want to identify this side, the one side with the 0 side. You want to do this. This is going to be a solid torus. But when you do this, you rotate one of the sides before the identification. You rotate by exactly that number, 2 pi q over p. So you give a rotation here, and then you glue together. This will be a Cyphered, this will be a fibered solid torus, and the fibration is going to be twisted, because think of this. You have here your standard fibration, like your, how's the word for that? Foliation. You have a foliation by parallel lines here. Like each point has a line, each point has a line, each point has a line. And now when you rotate and you glue together, you will have points, lines going into another lines, and lines going into another lines, until after P times you close up. Unless you are the central fiber. The central fiber is rotated into itself, so it's glued into itself. So you will have lines, circles, not lines anymore. You will have circles going around several times, while the central fiber is going around just one time. So that's why this core fiber is important. It's called the core fiber. And we say that it is regular if P is 1, so everyone is going around just one time, just like the central fiber. But if P is larger than 1, you will go around at least twice, and the central fiber will go around one time. Then it's called singular fibration. Yeah, that's the what's going on. Here is better. Picture time. I said I didn't like that definition, so I want to present it in a picture. You start with the unit disk, and here it is amplified, and you look at the solid torus. D times S1. And this disk, this solid torus, has a trivial fibration, which is this foliation by parallel circles, and it's just the trivial fibration of the solid torus. But it's not the only one. We can have several decompositions of this same object by circles. And yeah, it's not the only one. So let's look just at the boundary for now, just at the boundary of the solid torus. And at this point, I think it's essential that we look at the boundary of D cross S1, not at the boundary of D cross S1. It's a little subtle, but if you look at the boundary of D cross S1, you have one S1 different from the other. This S1, which I'm looking at the boundary, it bounds a disk in the inside of your solid torus. The other doesn't. So this is something to always keep in mind. If something is the boundary of something, don't forget that, because it might be helpful. Okay, you look at this, and this is a torus. So now we will look at it in this R2 representation, where the left side is this the left side? Yeah, this is the left side. Where the left side is identified with the right side, and the bottom is identified with the top. And in this torus, we know the fundamental group. The fundamental group is generated by P and Q. You have these curves called the PQ curves. You go around this P times, you go around this Q times. And the picture here is a lot simpler to understand as the picture here. You cannot see that this is gamma 3,2, but here you can see that this is gamma 3,2. It's going around 3 times in this direction and 2 times in the other direction. So you take your pair of PQ integers, coprimes, and you have this element of the fundamental group of phi1 of the torus. And now what you do is this element is you look at it in the boundary of your solid torus, and you push it. You push it to the inside just a little bit. Just a little bit. It was an embedded curve in the boundary of your manifold. So it's going to be an embedded curve, at least when you push it a little bit to the inside. And now you want to see how it intersects your disk. Never forget you have a disk. This is important. So it's going to intersect your circle. I never remember if it's P times or Q times. It's P times. It's going to intersect that disk. It's going to intersect that disk exactly P times. So our example here, gamma 3,2, is going to intersect your disk 3 times. So here are the 3 points where this gamma intersects. And we can do everything like in the most symmetric possible manner so we understand it. And what happens is that you divide your disk into P sectors. For each sector, you only have 1 point. Now you think in these sectors, what are the other curves when I start to make isotopy of this curve? Like you pushed it a little bit to inside, but now you can push it higher. You can like rotate it a little bit. You can keep doing this kind of things. And what you're going to see is that for any point in the sector, you will have corresponding points in other sectors, and you will have a fiber which goes around 3 times or p times in this case. And the picture is going to look a little like this. When you change the point, you change this fiber rotating around the central core. And it's going to rotate p times around the central core, while the central core only rotates once, only goes around it once. It's like a triple cover, or p cover, right? You have curves going p times, while the central is only going 1. I rather look at it that way than the theoretical definition one. It's more geometric. It's harder to prove it's well behaved. It's harder to prove it's well behaved. Yeah, you're right. And now we have this definition of regular versus singular. It's singular if other fibers are going around more times, and it's only going around once. Okay, so let's make the definition of Cyphered fiber spaces. Now, finally, we can make the precise definition. Now we know the local picture, and the definition is like this. A Cyphered fiber space is a compact, possibly with boundary to a manifold, that admits a decomposition into circles. And these circles are going to be the fibers, such that any fiber has a neighborhood made of fibers with the structure of some torus TPQ. So this is the definition of a Cyphered fiber space. And there are people looking, what? And okay, yeah, fiber is regular if the neighborhood of it is regular, singular, if the fiber is singular. I will give example in 1 minute, okay? So some properties. Let n be a compact tree manifold, then n is Cyphered fiber if and only if it has a foliation by circles. So it's not just a decomposition by circles, it's going to be actually a foliation. This is a result by Epstein. And in this case, you can also prove that n will only have a finite number of singular fibers. Generically, any fiber is going to be regular, except for a finite number of fibers that are not regular, they are singular. Okay, so let me give you an example of a Cyphered fiber space to have something in your mind, right? Because so far it's a little theoretical, too much theoretical. Let's start with the unitary cube in R3. Yeah, this we understand. This even I understand. Okay, you start with this cube and we will identify front and back and left and right. So when we make these identifications, we have a torus, cross, and interval. That's all, because we are identifying front and back. So for each horizontal slice, it's a square. We are identifying the sides of the square. And for each left and right, we are also identifying, and we are not making any change on the orientations. We are identifying them. So it's going to be a torus, cross, and interval. In particular, these 4 red points here, they are all the same point, and these 4 blue points there are all the same point. But this manifold has boundary. This is already Cyphered fiber, because you have a lot of circles in there. But it has boundary, and we want something without boundary. So we need some identification top to bottom. Top to bottom. If we just do trivial one, we will get the 3 torus, and that's cheating. Let's do a more interesting one. Let's identify top with a rotation of pi with the bottom. Now what's going on? Let's look at this manifold. Now these 8 points are the same, because you take this point here, it's identified with this point here. The front left is identified with the top right point, bottom. And now this point was already identified with the other three, so it's all the same. And we have these 8 points are the same. So this is more or less the picture of what we are making this identification from the top to bottom. We have this axis, and if you have an axis of rotation, this is going to be a singular fiber already. And we are identifying points here with points rotating around this axis up. Okay, I am claiming that this is a Cyphered fiber space, so let's try to look at the fibers. First fiber I already showed to you is the central core. This central fiber, when you identify the 1/2, 1/2 to the bottom, you rotate, you stay in the same point. So this is now an S1 curve. This is now a simple closed curve. Okay, let's look at the other fibers. You take any point here, x, y, 0, and I should have said that x and y are also not 1. We are not in the boundary. The boundary is going to be more difficult. So we are an interior point on this square, which is not the central point. So this point is identified with this other point. When you rotate and you go up. This is the identification. And now you look at this vertical line over this point. When you reach the top, it's not closed because this point is identified with this other point here, and the fiber keeps going. And now this is a simple closed curve because the blue dots are the same point. This point is the same as that point. So here I started going vertical, I exit here, and now I close up. So this is a vertical fiber. And now you already see that this fiber is different from this fiber. This is a singular fiber. This is going to be a regular fiber. Eventually, I'll show that to you. Okay, now let's look at the fibers in the 4 corners, in the 8 corners, and they are the same point. So yeah, it's just this 4 vertical segments, but they are not 4 segments. They are 1 segment represented 4 times. They are all the very same segments. If you have an ant walking in this segment, you will see this ant walking at the same time in all 4 segments. They are the same point in space. So it's only 1 segment. The blue one I showed you before, they were 2 segments, distinct segments. Okay, the middle point of the front face. This point is identified with the middle point of the back face by the first front to back identification. So these 2 points are the same point. And this point on the back is also identified with a point on the front up when you rotate. So you have a 3rd point here. And you also have a 4th point there by the identification again, front to back. So these 4 points are the same point, and they are all the times it appears on space. Now let's look at the fiber. You just look at this vertical segment, and you have 2 vertical segments, but they are, again, the same segment, just pictured twice. It's not 1 segment that exits here and returns here. They are actually the same. They are walked at the same time. Okay, what else? The same thing for the middle right and the middle left. And now all that remains is something which is in the boundary, in these faces, but it's not the corner or the middle. So you take any point like that. I'm choosing it to the front face just to paint a picture. And this point, by the identification front and back, is the same as that point. And by the identification bottom and top, you rotate, and then you identify again top and bottom, and it's that other point there. So this point appears in your manifold 4 times. And we can look at this vertical segment. First, this vertical segment here, it starts here in this point and go up there. And it has to reappear in the back bottom. It reappears there. It reappears there and keeps going up. Now we just see this segment more times. Now we have 4 segments, 2 equal, 2 distinct. Like if you have an ant walking, it would appear only 2 times every time she looks. Like this point here is the same as that point there, but not the same as any other point. You are walking, walking, walking 2 times, and then you disappear here and you reappear down here. And now you are only, again, showing up 2 times here and here. So this is also going to be a regular fiber. Weird, but true. Okay. So this is a pictorial description of all the types of fibers. We have fibers, special fibers, like the central core. Oops. Like the central core. This red fiber, which appears 4 times. The blue fiber, which appears 2 times. And the green fiber, which appears 2 times. These fibers are fibers, if you notice in this previous picture, that they are bounded always by 2 dots, while the other fibers are bounded by 1 dot. So that's basically the distinction between these fibers and those fibers. Those fibers here, they only have 1 dot because you are disappearing somewhere, you are not finishing, you are not closing up, and you are reappearing somewhere else to then close up. So we have 4 singular fibers, and any other fiber is going to be regular. Let me show you the regularity of these fibers. It's not very difficult. If you are not one of those other fibers, you can be away from these other fibers by a definite amount. And in these small disks, any fiber is going to look the same as you. Remember, this pink line here, oh, no, not this one. This pink line here is the same as that one. So it's not appearing twice. It's appearing, this one is just 1 time. And here is half the neighborhood, and there's the other half of the neighborhood. So the blue neighborhood and the pink neighborhood are exactly the same. They are not different. So these are actually regular fibers because in these neighborhoods, everybody goes around the same amount of times. And in the singular fibers, I will just use the example of the central core. What happens is that any neighborhood of the central core is the only one that goes around only once. Everything else goes around twice. So they have a structure of this fiber torus T21. So this is the non-trivial example of a Cyphered fiber manifold. What are
the 4 singular fibers?
The 4 singular fibers. Good question. Okay, let's.
In the middle.
These are the 4 singular fibers. Go by color. We have one in the middle, the black one. You have one which is the green one. That's 2. We have one which is the blue one. That's 3, and the red one, which is 4. All the red ones are the same, just appearing more than once in space. So
I don't know, like, but I can take that long surface using
that would be Cyphered fiber. Yeah, that's basically the first main example of a Cyphered fiber space. And we will actually, maybe today, show all the Cyphered fiber spaces. Yeah. You like that, right? Yeah, they are classified. Okay, so these are I think this is a little better now. Well, I think I went a little fast here. These are just 4 fibers. These are the 4 singular fibers. Okay. So far, we have definition of a Cyphered fiber space, check. We have an example of a Cyphered fiber space, check. And now we need one property, which is the Cyphered fibration, and then we will present a general construction, and this general construction actually gives a complete classification. And complete is a quote unquote because it is up to isomorphisms. It's not up to diffeomorphisms. The classification up to diffeomorphisms is heavier, it's more difficult to achieve, and it follows from this construction by later seeing which ones of these manifolds that we build might have distinct Cyphered fibrations. Okay, so okay, up to isomorphisms. So let's present this property. Let M be a Cyphered fiber space, and let X be the topological space obtained by collapsing every fiber into a point. So first, we need to think that, okay, I am collapsing every fiber to a point, then at first I am just a topological space. You have the notion of a neighborhood of fibers. Cyphered fiber spaces have neighborhoods of fibers. So you have neighborhoods of points in this other space that you are downstairs. So this is a topological space. You have the notion of nearby fibers, so you have the notion of nearby points. You don't have much more by now, but what happens? Oh, yeah, that's the definition of the topological space. And the proposition is that you have a lot more. You are not just a topological space, but you are a good orbifold with a finite number of cone points. Okay, if you don't know what a good orbifold is, I didn't know either, but intuitively, a orbifold in dimension 2, it's easier. A good orbifold is just a surface with singularities. Like you might have a corner, like you take two planes intersecting in an X, and you just take one of these V's. This is going to be an orbifold with this singularity here forming.
What's the surface?
What's a surface? No. Everything is differentiable. Everything is differentiable.
But you put a net on it.
No, not yet. I just have a differentiable structure.
There's no singularity in dimension 2.
A point where it's not smooth. It's a surface. It's almost a surface.
It's smooth. It's diffeomorphic and it's smooth. It's not metrically smooth. It's smooth.
It's not metrically smooth.
Dimension 2, but dimension 2, the orbifold is smooth.
Yeah, that's why I thought topological texts are so hard to read. I don't follow.
If you play the circle, I see the group, you still get the circle.
Okay.
It's not singular.
Okay, so let's think they have metrics. Then maybe it's better. Okay, I think I will be able to explain what I mean by singularities in a few seconds, in a few moments. So an orbifold, in my point of view, is just a surface where this point loses the differentiable structure of R2. It's a different structure where this structure is no longer the same as the open disk in R2. And a cone point is going to be defined soon. Okay, so using this proposition, I will give you an intuition of why it's true. And then the definition of a good orbifold with a finite number of cone points is going to be a little more clear. And the definition is that this collapse of M into this space of all the fibers is going to be called the Cyphered fibration. And X is going to be called the base space of the Cyphered fibration. And M is going to be this total space of this bundle over X. So actually, the question that you made before, it's here. A Cyphered fiber space is going to be not exactly just a product, but it's going to be an S1 bundle. For each point in this orbifold, you have a circle, and in the total space, it will smoothen out the singularities of the orbifold, and you have something like that. Okay, so let me give you the pictorial description of the proof, and I hope this will make it clear what I mean by singularities, by by singularities, by points of non-differentiability. Let X be a point in this abstract topological space, and let gamma be its ciphered fiber. So here you have a point in this topological space so far, and here we have a fiber. Let's think as in the previous example, just like a segment glued together by the boundaries. So this fiber is either regular or singular. If this fiber is regular, you have a tubular neighborhood around it made of fibers, and each fiber intersects, goes around this neighborhood only once. You have a standard fiber torus, a trivial fiber torus. Everything goes around once, and you don't have anything really complicated going on. So you have this cross-section, which descends to a cross-section in X in your topological space. And now you can just push the differentiable structure from this cross-section to X. And this is going to be a neighborhood of a point in R2. It's going to be just a disk in R2. So this is going to be a regular point. If the fiber is not regular, but is singular with multiplicity P, then a neighborhood is going to look a lot like this. You will have one core fiber and P segments going around. For each point, it's going around P times. So in this cross-section, what you see is points being identified. But it's a finite number of identifications. And again, we cannot work with the sectors, just like before. We have this P sectors in your neighborhood, thinking of it as this cross-section. And the identification is going to be like this. Each point here is going to be identified with one point of the other, one point of the other, one point of the other, for every point in this triangle. And now this triangle closes into itself as this boundary goes to this boundary. So this is going to be, oh, and here we have an angle, an equal angle to pi time, divided by P. And I have like this, and then you close it together, and you get a cone. This is going to be a differentiable structure of a cone. That's what it's not differentiable at the singularity, but that's what I mean by a isolated cone point of multiplicity P. I hope this gets a little better. As I said from the beginning, topologists, excuse me, I am probably making assumptions that I'm not even aware that I am making. Now you understand why I said that. Okay, so this is the structure around singular points. If you have a regular point, you have a surface, neighborhood of a surface. If you have a singular point, you have this cone. So you are an orbital. Let's go for our previous example and see what is the orbifold in this example. We need to collapse the fibers into a point. So the best strategy here would be to choose representatives. So we need to choose one area of this cipher fiber space for which every fiber crosses. I don't know, maybe this part here, this top half of the top square in these coordinates is a good way of working, because every fiber goes through that square, not square, that rectangle, but some fibers go a little more than one time, go 2 times. But let's look at this space here. To obtain the orbifold, we just need to look at the identifications of the fibers in this space. In the interior of this rectangle, any fiber is going to reappear only there, outside. So in the interior of this rectangle, any fiber will intersect only one time. So there is no identification here in the interior. All the identifications are going to be on the boundary. And now we need to understand what is these identifications on the boundary. What are these identifications on the boundary? First, we know from our construction of the previous manifold that left and right are associated by definition. So yeah, left and right are going to be associated. Now we can look at this little segment, this half segment, and see what happens to this segment. One point here, let's see, what's the next one? No. One point here is going to be associated to the bottom. So let's think of it there. No, not there. There. That's the bottom. By front and bottom association. And now the fiber that goes to that point is going down and is going to reappear right here on the top. So actually, this segment here is going to be associated with this segment here. And we could think that this is the right orientation because when you rotate 180 and you are next to a corner, you reappear next to the other corner. But actually, it's much more easier to think like, yeah, it's got to connect a red dot to a green dot. So yeah, let's connect the red dot to the green dot. That's the only way of doing this orientation. And the back is going to be similar. We are going to have a point here on the top. It goes down to the bottom part. And then you rotate 180 and you bring it up. And it's going to be on this other half here. And here's the identification. So our space, our orbifold, is going to be obtained by this rectangle with these identifications along the boundaries. So I don't have out here. So if we have here our rectangle, we need to this boundary to this boundary, but we also need, it's not going to be a torus because it's not this circle with this circle. It's going to be like this. Here we have a cone point. It's going to be a corner. And here we're going to have another cone point, a corner. And all the four sides are going to be identified, but the middle is not going to be identified. Nothing here is identified. So actually, what you see is a fold over this line, and you have this pillowcase shape. This is called a flat sphere. We can put a metric of 0 curvature in this object, but it's not going to be smooth in these four corners. And 4 cone points, and this is called the pillowcase orbifold. So this is the example of our first cipher fiber space collapsing into a orbifold, and that's very cool. I don't know, I like it.
Hello.
Yeah. Sure.
In this picture, does the angle equal to?
It's pi over 2. Yeah, no, pi. It's pi. The angle is equal to pi.
So
yeah.
Yes,
yeah, that's not the right picture. This is just because this is flat, right? It's not going to be able to.
I'm sorry, this was what is the orbifold associated to actually a plain solid? I mean, a solid curve is a side of the mind.
It's just going to be the disk. It's just going to be the disk.
You don't have singular points.
Unless you have, I mean, if you are with the trivial fibration is going to give you the disk. But if you have these vibrations which go around more than one time, you're going to see a cone. You're going to see one point and a cone. And the angle of the cone, the more the fibers spin around, the closest the cone will look like. It's going to be like more and more singular. Eventually, if you have like the sequence, it will converge to like a segment or something. If you have sequences of things spinning more and more, you will converge to like this really thin cone, which will collapse into a line. segment. Yeah.
Do we like have a free manifold which is not product, like forming your surface, but for which that space active maximum smooth thing?
Yes, we can have an example like that. And actually, I will show it to you. I don't think I will show it to you today because it's going to take a while. So I will actually stop here today, and tomorrow I will start answering that question and give you several examples of that. Okay, so thank you all. Oh, yes, right. Let's see if there are some questions. Is there anyone there? Like the Pink Floyd song, right? Is there anybody out there? Yeah, 37. I can see the chat, but I just wrote in the chat questions. Anyone sees the chat? I see a hand up here, but I don't know how to do it. If anyone wants to unmute and ask the question, I see there are, yeah. Here, Oliviero, you want to make a question? No, he's muted. Oh, yeah, Mateus, valeu. Thank you for the message, but everyone is seeing your message. It's sent on private. So everyone can see your message. See, Mateus? Okay, so thank you all then.